So I'm going to write down the pertinent details here. I'm not going to do it in full engineering format just because that would take too long. But in problem 2, we have a YY system where our line voltages measured at the load are 208 volts RMS. And our line currents have a value of 6 amps RMS. We are told that the total average power absorbed by the three-phase loads, so that's going to be P three-phase, and I'm putting an L to let us know that it's at the loads, is 1,800 watts. And we are asked to determine A, the power factor at which the loads operate, and B, the load impedance per phase, ZY. So before I just show you guys how to do this, does anybody have any thoughts on how we might approach this? So in part A, we are asked to find our power factor. So I would like for you guys to do me a favor and go back in your notes, and you might have to go back to your single phase power notes and tell me what the definition for power factor is, because we had 2 different ways to represent power factor. Okay. So P average over apparent power, not complex power, the magnitude of the complex power. And then what was the other one? Our power factor angle, theta S. Okay, thank you, Ricky. Absolutely. Those are the 2 relationships that I'm looking for. So if we want to calculate power factor, we're going to wind up having to do one of those 2 things. Okay. So which of those 2 relationships do we have some of the information for already? Let's start there. So the average power, right? So we were given the average power, the total average power absorbed by our 3-phase load. So we could easily find the average power on a single phase of our load simply by dividing P 3-phase by a factor of 3, right? So this is going to look like 600 watts. Now, how might we go about determining our apparent power absorbed by a single phase of our load? So yeah, so the apparent power is literally just going to be our line voltage times our line current. Okay. Well, so let me actually, I'm gonna change this slightly. So I put the 600 there because I was looking at it on a single phase basis. My problem with line voltage and line current is that if I want my total complex power, that's going to be multiplied by √3, and so it's not going to be an easy thing to divide by 3. So what I'm going to do here, instead of just doing the average power for a single phase over the apparent power for a single phase, is I'm going to do the average power on our 3-phase system divided by our apparent power in our 3-phase system, and that's going to give me the power factor as well. Okay. So sorry about that hiccup there. 1,800 watts divided by √3, And then here I'm going to put 208 volts RMS, and here I'm going to put 6 amps RMS. Like so. And if I throw that into my calculator, 1800 over root 3 multiplied by 208 times 6, I get 0.83272 and some change. So if we go back to, let me put this in a different relationship, right? So our total complex power in a three-phase system can either be written as 3 times our phase voltage times our phase current with an angle of the impedance, or it could be written as the square root of 3 times our line voltage times our line current with an angle of our impedance. Well, this guy right here is simply the magnitude, which is our apparent power when we have phase quantities. And this guy right here is our apparent power when we have line quantities. Since I gave you a line voltage and a line current, we should be using that relationship. We derived why there is a excuse me, why there is a factor of square root of 3 there instead of 3. I want to say that would have been like last Thursday's class meeting. But it goes into the fact that in a Y-connected system, the line voltage is related to the phase voltage by a factor of square root of 3. And in a delta-connected system, the line current is related to the phase current by a factor of square root of 3. So I have my total average power. And from this, I determined my power factor. But I only determined the magnitude of my power factor. And so what I'm trying to suss out now, based on the information that we were provided, is whether this power factor is a leading quantity or a lagging quantity. Now, so what's positive? So the power factor is always going to be a positive quantity when we're dealing with the power absorbed by a load. Okay. Okay. So let's see. So if we do, well, so the inverse cosine of this guy is going to give us an angle of 33.6211 degrees, right? So I could say that, let me do it, I guess, in purple here, right? So theta z is the inverse cosine of our power factor, which in this case came out to be 33.621 degrees, which is indeed a positive quantity. I'm slightly concerned that since the inverse cosine can, as far as I know, only give me positive values, I'm a little bit worried. But I don't see any more information that's jumping out at me specifically that would tell me that we would expect to have any type of capacitance in our system. Let me just reread things really quickly here. So in a balanced three-phase YY system, the line voltages measured at the load have a magnitude of VL. The line currents have a magnitude of 6 amps RMS. The total average power absorbed by the three-phase load is P three-phase L. Just determine the power factor and the load impedance per phase. So I think this is literally the best we can do, is we're just going to assume that because this angle was positive, we're going to wind up having a lagging power factor. Realistically, I think I needed to include like one more small piece of information to make that a definitive thing. But based on my answer for part B, it would make sense that we would have a lagging power factor. So here is our result for part A. So how could I now determine my impedance per phase? So Brock, you're raising your hand? So we have a line voltage and a line current. If we had a phase voltage and a phase current, I would agree with you wholeheartedly. But we have enough information to treat it like a phase voltage and a phase current because we're told specifically that it is a YY system, right? So in a YY system, let me just draw a picture here to remind you guys of this, but I believe you already know it. Oops. So this is a simple representation of a YY system. We don't know what any of these impedances are as of yet, but that's not really important for what I'm trying to show you guys here in a second. So this is my line current, IAA, and I've been given the magnitude of that line current, right? This is my phase current, IAN. So how is that line current IAA related to that phase current IAN? They're the same thing, okay? So because I have a Y-connected system, I know that my line currents and my phase currents are literally the exact same thing. So I can say very easily that my phase current IP magnitude is going to be the same thing as my line current magnitude IL, which is 6 amps RMS. Okay. Now, we were also given that the magnitude of this voltage right here is 208 volts RMS, right? That's what our line voltage at the load is. Okay. Well, how is that related to this phase voltage, VAN? Right. So VAN is going to be square root of 3 times smaller than VAB. Okay. So I could say that VP is equal to VL. Let me say VPL is equal to VLL. So this is the phase voltage at the load is equal to the line voltage at the load divided by square root of 3, which should come out to be approximately 120 volts, but we'll double check it just real quick here. So this is 208 volts RMS over root 3. Let me scroll up and make sure that that is indeed 208. Yep. So we would have 208 divided by the square root of 3 gives me 120.089 volts. Okay. So I now know my phase voltage. I know my phase current, so that gives me the magnitude of my impedance. How am I going to figure out the angle of my impedance? So V over I is the magnitude. I'll give you a hint, we already have it. So the power factor angle is the same thing as the angle of the impedance. And it literally always has been. It's just theta V minus theta I, right? So essentially, our impedance ZY is just going to be VPL over IP with an angle of theta Z. So that's going to look like 120.089 volts RMS over 6 amps RMS with an angle of 33.621 degrees. Which is going to look like, let's see, so answer over 6. 5.604 with an angle of 33.621 degrees ohms, or in rectangular form, 4.666 plus J 3.103 degrees. There's going to be 103 ohms. That is wildly different than the result that I have here from when I worked this problem. Okay. See what the problem is. Okay, sorry. Let me try this again. Yeah, it's me using the answer thing in my calculator too often and forgetting what the actual answer was. Thank you for that. Let me look at this again. All right. So 208 divided by root 3. I'm going to store that in my calculator as y. So y over 6 with an angle of x 20.0148, so 20.015 with an angle of 33.621 degrees ohms. And then in rectangular form, 16.667 plus J 11.082 ohms. Thank you for that catch. I appreciate it. Yeah, totally calculator error. Nothing wrong with the process. Just me not being awake enough to use my calculator correctly this morning. My apologies. So for what it's worth, I'm going to make a note here. To include the word inductive load in the problem statement so that this will no longer be an assumption, so that this works out. Okay. But this is problem 2. So we solve for our power factor using our average power and our apparent power, which we haven't used that relationship to do it very often, but it is the fundamental definition by which power factor is defined. Then we figured out what our impedance was, and the hard part of this guy is remembering that whenever I have my line voltage, this guy, and line current, that ratio is not going to be the magnitude of the impedance, because that line voltage on that Y-connected load isn't the voltage drop across the impedance itself, right? And similarly, if we had a delta connected load, our line current wouldn't be the current flowing through each phase of the load. So it's never going to work out correctly to calculate impedance using line quantities. We always need to use phase-related quantities. All right, any other questions about this problem right here? Hopefully problem 3 and 5 goes a bit more swimmingly because my head is slightly less up my ass. We'll see. All right, so let's look at problem number 3. So in this particular problem, we are told that there is a shopping center that contains 4 stores representing balanced 3-phase loads. So for load number 1, we are given that it absorbs 400 kilovolt amperes at a power factor of 0.9 lagging. Load 2 absorbs 150 kilowatts at a power factor of 0.85 lagging. Load 3 absorbs 100 kilowatts at a power factor of 0.95 lagging. And load 4 absorbs 100 kVA at a power factor of 0.95 leading. We are told that the power lines that service the shopping center represent a 3-phase source with a line voltage magnitude, so VLS for the line voltage at the source is 13.8 kilovolt RMS at a frequency of 60 hertz. If the impedance of the power lines is negligible, we are asked to determine the magnitude of the line currents flowing through the power lines. So we're trying to find IL, the power factor at which our power lines are supplying power. So this is the power factor at which the source is operating. And the size of the capacitor bank needed to increase the power factor to 0.975 lagging. So let me just make a note over here. PF new is equal to 0.975 lagging, and we're asked to find the capacitance CY. Okay. So we are going to find our line current, and we're going to find the power factor at which our source is supplying power by determining the total complex power absorbed in our system, right? So that'll just be total complex power of those 4 loads added together, okay? So let's say that we have complex power for load 1. I'm going to call it S1. So how might I go about determining the complex power absorbed by load one based on the information that's given.
Just find the, well, it gives you the 400 kVA, so they define its angle, so don't take the inverse cosine of the power factor.
Exactly right. And I want to commend you for recognizing that we were already given the apparent power, so we don't need to do anything for that part. That's one of the most common mistakes that I see. So if you're given the number in kilovolt amperes or volt amperes, you don't have to divide by a power factor because you already know what the apparent power is. So it's literally just going to be 400 with an angle of the inverse cosine of 0.9. So I got 400 with an angle of 25.8419. So let's call that 842 degrees. It's 0.9. My penmanship is just shitty. And I'm going to store this in my calculator for later as X. So somebody else tell me how we're going to do the complex power absorbed by load 2. It's not the same thing because our power was given to us in watts. Exactly right. So we take the average power and divide it by the power factor to give us our apparent power. And then from there, it's the same thing. So that'll be 150 divided by 0.85 with an angle of the inverse cosine of 0.85. And I got 176.4705. So let's call that 471 with an angle of 31.788 degrees kilovolt amperes. And I'm going to store this in my calculator as Y. Okay. For load number 3, we're going to do the exact same thing as we did for load number 2 because we're provided with essentially the same information, right? We have average power and we have power factor that is lagging. So that's just going to look like 100 divided by 0.95 with an angle of the inverse cosine of 0.95. And I got 105.263 with an angle of 18.195 degrees kilovolt amperes, which I'm storing in my calculator as Z. And then lastly, for load 4, it's going to look very similar to what we did for load number 1, except that now our power factor is leading. So how do we modify our expression to handle a leading power factor?
Negative.
We put a negative sign in front of the inverse cosine function. Good job. So that's going to look like 100 with an angle of negative inverse cosine 0.95, which should be 100 with an angle of negative 18.195 degrees kilovolt amperes, and I'm going to store that in my calculator as T. So the total three-phase power absorbed in our system is just going to be S1 plus S2 plus S3 plus S4 all added together, right? So in my calculator, that's X plus Y plus Z plus T. And I got 754.563 with an angle of 20.882 degrees kilovolt amperes, which for what it's worth, I'm going to store as A. And for reasons that I hope will be obvious in a moment, I'm going to also choose to express this in rectangular form. And I get 705 plus J 268.961 kilovolt amperes. Okay, so which one do you guys want to do first? Line current or power factor? Line current, okay. So I'm going to scroll up here. So we know our total complex power in both polar form and rectangular form. So we have access to apparent power, power factor angle, average power, and reactive power. We were also told what the line voltages at our source were, and we were also told that there is no transmission line impedance that we need to worry about. So those are also the line voltages at our loads, effectively. So I'm asked to find the line current, and I just want to scroll up here because I already have those relationships written down, right? So I know my total complex power and therefore my apparent power. I know what VL is. √3 is just a constant. So it seems like the magnitude of my line current is just going to be my apparent power divided by √3 times VL. Okay. So we could say that IL is just the magnitude of S3 phase divided by √3 times VLS. So that's going to look like 754.563 kilovolt amperes divided by √3 times 13.8 kilovolts RMS. And I wound up getting 31.5686. So let's call this 569 amps RMS. So that is the magnitude of my line current. Anybody have any questions, comments, or concerns about that calculation or where that relationship came from? Sure. So I'll write it down on this page so that we can look at it, right? So earlier in today's class meeting, I reminded you of a relationship that S3 phase is equal to 3 VP IP with an angle of theta Z, or √3 VL IL with an angle of theta Z. And this part right here is the apparent power, which is just the magnitude, right? So if I have my apparent power is equal to √3 times VL times IL, then I could rearrange that guy to find that IL is just my apparent power divided by √3 times VL. All right, so any other questions about that calculation before we move on to power factor? Ricky, how may I help you?
So, while single phase, you don't have to worry about it.
Right, and if it was single phase, we wouldn't have a VL or IL to deal with. We'd only have phase quantities, right? So that 3 out front of the VP IP is 100% because it's a 3-phase system. That √3 comes from the fact that I can split that 3 into square root of 3 times square root of 3. And then I know that in a Y-connected system, my line currents and phase currents are related by √3. And in a Y-connected system, my line voltages and phase voltages are related by a factor of √3. And in a delta-connected system, my line currents and phase currents are related to each other by a factor of √3. And again, we derived all of that, I believe it was last Thursday. Any other questions or comments about this particular calculation? All right, so how do we get our power factor? Cosine of the angle, absolutely right. So the angle that we have is 20.882 degrees. So the power factor at which our source is operating is simply the cosine of 20.882 degrees which I get to be 0.934 for what it's worth, 32. Is this power factor leading or lagging? Lagging because the angle is positive. So in order for us to answer part C here, we're going to have to use our equation for finding C in a power factor correction thing, right? So I'm just going to write that equation down here to remind you all of what it is. So C in general is going to be our single phase average power multiplied by the tangent of theta old minus the tangent of theta new, all divided by omega times the magnitude of the voltage drop across the capacitor squared. Okay. So theta old is just the 20.882 degrees that we already have. Right? Because that was our angle before we applied our power factor correction capacitor bank. Okay. Theta new is just going to be the inverse cosine of our target power factor, which is 0.975. Which comes out to be 12.836 degrees, which I'm going to store in my calculator as B. What is our single phase average power going to be? Let me scroll up. Oh, absolutely right. So which one of those is the power that I'm dividing by 3? The 705. So the average power or the real part of the complex power in rectangular form. So 705 kilowatts over 3. I'm just going to leave it like that for now. All right. what's omega going to be? So we were told here in our problem statement that our frequency is 60 hertz. So omega is just 120 pi, 2 pi times f. Absolutely right. And then the last thing we need to figure out is the magnitude of our capacitor voltage, right? So we're told specifically that we want a Y-connected capacitor bank. But we have a line-to-line voltage. So how are we going to make that look like a line-to-neutral voltage? Divide by √3. Absolutely right. So just 13.8 kilovolts RMS divided by √3. So I get 7,967.434 volts RMS. And I'm going to store this as C. So if I plug things into my equation for calculating C, I'm going to have 705 over 3 times a factor of 10 to the 3, so that I'm just putting it in watts instead of kilowatts, right? Then I'm going to have the tangent of 20.882 degrees minus the tangent of 12.836 degrees, all divided by 120 pi times 7,967.434 volts RMS squared. So give me a moment to just put that in my calculator. So I got 5 zeros and then 1508. So I'm going to multiply that by 10 to the 6th. And I get 1.50834 microfarads. Any questions about that capacitance calculation? So the last problem that I want us to look at is number 5. So in number 5, we are told that we have a balanced 3-phase induction motor, and it is supplied by a Y-connected source where VAN is equal to 277 angle 0 degrees volts RMS at a frequency of 60 hertz. When connected to watt meters for power measurement, watt meter number 1 reads, so this will be P1 is 4.8 kilowatts. And watt meter number 2 reads 10.2 kilowatts. We were asked to determine the total complex power absorbed by our motor, so that'll be S motor. And we are asked to find the value for a delta connected capacitor bank if we want PF new to be equal to 0.98 lagging. So we've only used these relationships for one example problem so far, so I'm going to do most of the heavy lifting here. Okay. So the last example problem that we worked last Thursday was related to the 2 watt meter method. And we effectively did a similar calculation to this, except that we had some intermediate steps, right? So the first thing that we did was we added powers P1 and P2 to find our total average power. Then we used our relationship to find our angle and our power factor from that. So we're going to do that same thing. Okay. So theta z in this case is going to be the inverse tangent of the square root of 3 times P2 minus P1 over P2 plus P1. So that's going to look like the inverse tangent of root 3 multiplied by 10.2 minus 4.8 over 10.2 plus 4.8. And when I put this into my calculator, I get 31.945 and some change degrees. From this, we can say that our power factor for our motor is just the cosine of theta z. By the way, I stored this as x. So if I do the cosine of x, I get a power factor of 0.84856. And this power factor is lagging because our angle is positive, but we should have expected a lagging power anyway, a power factor, because we were told that it's an induction motor, which is always going to have a lagging power factor. So from here, we can say that the total complex power absorbed by our motor is just going to be P1 plus P2, that's our total average power, divided by our power factor with an angle of the theta z that we already determined. Okay. So that's going to look like 10.2 plus 4.8, all divided by 0.84856 with an angle of 31.945 degrees. And putting that into my calculator, I get 17.677, angle 31.945 degrees, kilovolt amperes. And I'm going to express this in rectangular form as well. So that's going to look like 15 plus J 9.353 kilovolt amperes in rectangular form. So we got our answer for S motor. Now we have to calculate C delta, right? So we're going to use the exact same expression that we used a moment ago to determine our capacitance. So that's going to be our single phase average power multiplied by the tangent of theta old minus the tangent of theta new, all divided by our angular frequency omega multiplied by the magnitude of the voltage drop across the capacitor squared. Okay. So what's our single phase power? You pointed at it, but you're not saying anything. 15 divided by what? 3. Yeah, exactly right. So it's just the real part of the complex power over 3. So 15 over 3 is just 5. So 5 kilowatts. Okay. What's theta old? (31.945 degrees. Great job. How am I going to find theta nu? So the inverse cosine of 0.84856 is that 31.945 degrees. Exactly right. So the inverse cosine of the new power factor after power factor correction. So inverse cosine of PF new I get to be 11.478 degrees. I'm going to store this as, actually, I'm going to store it as Z because I didn't write this down, but I stored this guy as Y earlier. What's omega going to be? Two pi times 60 or 120 pi radians per second. And then the voltage drop across my capacitor. So to be clear, this time I gave you a Y connected or a phase to neutral voltage, but our capacitor is in delta, so we need a line to line voltage, right? So to go from line to neutral, we divided by √3. So what do you think we're going to do to go the opposite direction here? Multiply by √3, which should come out to be something very close to 480 volts RMS. So √3 times 277 volts RMS is 479.778 volts RMS. And now I have all of the parts to put into my constituent equation, right? So that's going to look like 5 times 10 to the 3 watts, tangent of 31.945 degrees minus the tangent of 11.478 degrees, all over 120 pi times, I'm just going to leave this as root 3 times 277 volts RMS, square the whole thing. And I'm going to throw that into my calculator. So 5,000 times tangent of polar angle of y minus the tangent of z over 120 pi times root 3 times 277 squared. And I got data type error. Never seen that before, so what did I put in my calculator wrong? Apparently I forgot to store that 11.478 degrees as z, so it was doing it as a complex number. So let me do that real quick. Cosine inverse of 0.98. Store that as z. I get 4 zeros and then 24227. So that's going to look like 24.227 microfarads. All right, so we've worked 3 of those 5 homework problems for homework set number 3. We've still got about 45 minutes remaining. So I would be happy to answer any other questions you guys might have about the exam, or, anything other than just straight up working those other 2 homework problems. I'm going to leave those 2 to you guys. Yes, sir. That is correct. You can have an equation sheet. I don't like calling it a cheat sheet because that implies that you are cheating, and you are not, because I'm allowing you to bring this. So you get an equation sheet. I want to be very clear here. That is an 8.5 by 11 standard sheet of paper. Don't bring a legal sheet in or anything like that, like a jackass. Okay, so 8.5 by 11 sheet of paper, handwritten, front and back. You can put whatever you want to put on there. So you can put equations, relationships, worked out example problems. Just make sure that you can read it without any external aids. And so what I mean by that specifically is you can't write things so small that you have to bring a magnifying glass to read it. You can't write in both red and blue ink and then wear dopey ass 3D glasses to try to double the amount of information on there. Students come up with wild and ridiculous schemes. So I'm trying to cover my ass, just be a normal, rational person and make an equation sheet out for this test. Yes. So that's a fantastic question. So I'm going to essentially rederive that relationship for you just really quickly in terms of voltages and current. So hopefully it's explained. So if we looked on the source side of things, right? Let's say that we had a Y connected source. So here's our phase voltage VAN. Here's VBN. And here's VCN, right? Where this is terminal A, B, and C. This is my line to line voltage VAB, okay? So if I write a Kirchhoff's voltage law equation around this path, what I will get is negative VAN plus VAB plus VBN is equal to 0. Or just to be clear, when I'm writing a KVL equation, anytime I see the negative polarity terminal of a voltage first, it gets a negative sign. Anytime I see the positive polarity terminal first, it gets a plus sign. So that's where all of those signs come from, okay? I could rearrange this and I could say that VAB is equal to VAN minus VBN. And in a balanced three-phase system, I know that VBN is the exact same thing as VAN, just shifted by 120 degrees. So that's going to look like VAN times 1 angle 0 degrees minus 1 angle negative 120 degrees. And this guy right here is literally just the square root of 3 with an angle of 30 degrees. So that tells me that VAN multiplied by root 3 angle 30 degrees is my line voltage. So to go from a Y style voltage to a delta style voltage, we multiply by root 3 angle 30. And then to go the other way around, we obviously divide by root 3 angle 30. But now let's talk about currents because they're related by effectively that almost exact same thing, right? So on the load side of things, let's say that I have a delta connected load. So here's terminal A, B, C, and here is my C phase impedance, also Z delta. So let's say that I have some line current IAA flowing in, and then I have a phase current of IAB flowing out, and a phase current of ICA flowing in like so, where I've defined those phase currents to be flowing into the positive polarity terminal of those phase voltages that we talked about when we first introduced three-phase systems. So if I apply KCL at this node, I see that I have a current of IAA flowing in, a current of ICA flowing in, and a current of IAB flowing out. So putting my line current on one side and my phase currents on the opposite side, I get this relationship. And since my C phase current is going to be lagging my A phase current by 240 degrees, this is going to look like IAB times a factor of, let me do it this way, 1 angle 0 degrees minus 1 angle negative 240, right? So to be clear here, we used 1 angle negative 120 on the voltage because we were comparing it to the B phase. We're using 1 angle negative 240 here on the current because we're looking at the C phase, okay? Well, this thing right here actually comes out to be root 3 angle negative 30 degrees. And so from this, we can see that our line current in this case is simply our phase current multiplied by a factor of root 3 angle negative 30. So those are all of the different cases for multiplying or dividing by root 3 angle plus or minus 30. And if you can't remember whether it's plus or minus 30 or whether you're dividing or multiplying by root 3, you can always go back to those fundamentals of applying Kirchhoff's voltage law around a simple loop or applying Kirchhoff's current law at a node to get those relationships within a step or two. What else can I assist you guys with today? Yes, sir.
You said that that's only 2 course, 1 in class and 1 take home.
That's correct.
So when's the take home portion due?
So I'm going to assign the take-home portion on Thursday, and it will be due the following Thursday. So you will have 1 week to work like 3 to 4 problem stops. I haven't decided the full weight yet because I haven't made it out, but it's either going to be like 60% for in class and then the remainder for the take home, or like 70% for the in class and the remainder for the take home. So the majority of the weight will be your performance on the in class portion of the test. Yes, there will be partial credit for everything. And to be very clear here, when I am assigning partial credit, so what I am looking for, I want you guys to provide as much detail as you can. So if you just throw shit at, throw numbers at me with no explanation of where they came from, I can't really give you any partial credit because I don't know what you were trying to do. So write down the equations that you are trying to use and then put in your numbers and stuff like that. If you get the first part wrong, calculation wise, but your process is correct, I will only count off on that first calculation mistake. So I'm not going to continue to penalize. I'm not going to continue to penalize you for a mistake you made at the beginning of a problem over and over and over again. I try to be pretty fair about that. So if you just make some miscalculation, but your process is right, that is a relatively small error and you will lose a relatively small amount of points. But if you make different mistakes over and over again, then you're going to see that racks up. Does that make sense? Okay. So it's going to cover everything we've covered up until essentially today, but today was largely just example problems related to what we had covered last Thursday. I will say, though, that there will be more of an emphasis on the three-phase power portion of things. The single-phase power stuff was supposed to be a review of what you guys covered in your ENGT 221 class. So there will be more emphasis on the three-phase side of things, which is just applied single-phase relationships anyway. Yes. You know, originally it was my intention to do everything all math, but I think, and I'm not going to promise that I will actually take the time to do this, but a couple of conceptual questions asking about, relationships or something like that, on a multiple choice basis might be something that if I find the time to do it, I would like to investigate. So something like, true or false, the phase voltages and the line voltages in a delta connected system are equal to each other. Or true or false, the phase currents and the line currents in a Y connected system are equal to each other. That kind of just basic conceptual thing. Or, which of the following equations can be used to calculate power factor? And then I might give you a couple of different options and only, one or two of them will be correct, kind of thing. So nothing like, I don't think if I take the time to do it, it's not going to be anything crazy. It should be stuff that I've talked about over and over and over again, kind of thing. I don't believe in asking like super obscure questions and trying to trick you guys into losing points. That's an asshole's game. And while I'm an asshole, I'm not that type of asshole.
Scrolling up to that first part. Thanks.
If you make sure that you understand the homework, the test should be a good. So homeworks, ICAs, I mean, realistically, that's all the examples that you've been provided anyway, but that's where I'm going to go back to make the exam, is I'm going to look at what I've asked you to do in the homeworks, and then I'm going to attempt to ask you to do something slightly easier. So I like to make the exams easier than the homeworks because you have less time to think about things while you're doing it on the exam. That being said, I understand that the overwhelming majority of you guys don't even start on the damn homeworks until the day they're due anyway. So realistically, the amount of time you have dedicated to both things is similar. Ultimately, I'm going to try to make the exam slightly easier than the homeworks because it's a higher pressure situation and I don't want you freaking out trying to synthesize new material or anything like that. I think that's unfair to you guys. Yes, Brandon. Go for it, man. What about it? So the root 3 angle negative 30, you're only going to see if you are converting between a line current and a phase current in a delta connected system. So the negative 30 is for currents, positive 30 is for voltages. And the root 3 angle 30 thing is only for voltages going in a Y connected system. That's going from a line to neutral voltage to a line to line voltage or back and forth. So delta are always line to line. So line to phase doesn't really, yeah. So this VAB is measured between our transmission line terminals. So that is why it is a line to line voltage. This VAN, if I wanted to explicitly put the plus sign on this side and the minus sign on this side, this is a line to neutral voltage because it's measured between the transmission line terminal and the neutral terminal. Yes, Brandon. I will draw the circuits for you, even for the three-phase systems and all of that kind of stuff, just so that you don't have to spend more of your test time doing that. Yep. I like for you guys to have the practice of drawing them for your homeworks and all of that kind of stuff because it helps you think about how things are connected. But on the exam, where time is at a premium, I'll do it for you. I try very, very hard to make sure that that is the exam appropriate question on the end of course surveys is a damn near a 4. I'm a disorganized mess, but my exams, I try to really hard to make them appropriate and fair. Anything else I can assist you guys with for today? All righty. Well, you guys have a good rest of your day. I'm going to go hide in my office and try to make sure everything is uploaded and all that kind of good stuff for you guys to be able to study from. Make sure all the videos, all the ICA solutions, et cetera, are available. And yeah. Good luck. If you need any help with anything, don't forget about the tutoring session this afternoon, as well as just my normal office hours, both today and tomorrow.